Hello everyone and welcome back to Miss Chemistry, and today we're going to go over this first bit in thermodynamics, which is the Born-Haber cycles. And first we need to know about these thermochemical definitions. But before I go through that, please like and subscribe if you like this video and it helped you with your revision, please. And comment, please. Okay, so the thermochemical definitions. So you need to know these thermochemical definitions if you want to draw out these Born-Haber cycles and to answer these exam questions. So after I go through these, I recommend you memorize these and understand them. So the first definition is the enthalpy of formation. This links back to the topics in energetics in the year 1 topics. So energetics. So enthalpy of formation is the enthalpy change to form 1 mole of a substance from its elements in their standard states under their standard conditions. An example equation of this is sodium and chlorine, which makes 1 mole of sodium chloride. It's half a chlorine because you want 1 chlorine balancing equation. Next, we got the enthalpy of atomization. So this is something new. So the enthalpy of atomization is the enthalpy change to make 1 mole of gaseous atom from its element in its standard state. So this is just 1 element. And an example equation is chlorine. So we got half a chlorine, which is in its gaseous state, to form 1 mole of the gaseous atom, which is chlorine. And then here we have sodium. So this is from its standard state, sodium as a solid, which forms 1 mole of a gaseous atom of sodium. And as we're showing this example, this is also called the enthalpy of sublimation. So the enthalpy of sublimation is only for when a solid metal turning into a gaseous atom, and the enthalpy of sublimation is numerically the same as the enthalpy of atomization. So it'll be the same numerical value. So don't get confused if they say that in the exam question. Oh, I also forgot to mention that the enthalpy of formation is exothermic or endothermic. So exothermic meaning the arrows will go up, exothermic so the arrows will go down, and endothermic so the arrows will go up. And if the enthalpy of formation is exothermic, that means it's stable. Then the enthalpy of atomization is endothermic, so that means it goes up. The arrows goes up in the Born-Haber cycle. Next, you got the first ionization enthalpy, aka the first ionization in energy. This links back to year 1 topic, so better go through that. And you should know this definition by heart. So the first ionization energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of monopositive ions, which is 1+ ions. An example equation of this is sodium. So they're all in this gaseous state. And if you remember the equations, you can remember the definitions because you understand them. And also the first ionization energy is endothermic, so the arrows will go up. Next, we got the second ionization enthalpy, which is aka the second ionization energy. Basically the same definition, but just using the monopositive ions and the 2+ gaseous 2+ ions. So the second ionization energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous monopositive ions to form 1 mole of gaseous 2+ ions. An example equation of this is sodium, but this time it's a monopositive ion, so that means it's 1+, sodium plus, on its gaseous state to the Na2+. And it's also endothermic. So both of the ionization energies, the first and the second ionization energy, is endothermic, so the arrows go up. Next is the first electron affinity. So the electron affinities is basically the total opposite of the ionization energies, okay? So the first ionization energy is the enthalpy change of when 1 mole of gaseous atoms gains 1 mole of electrons to form 1 mole of gaseous mononegative ions. So an example is chlorine, and chlorine is a gas. So this is the gaseous atom gaining 1 mole of electrons to form 1 mole of gaseous mononegative ions, and the first electron affinity is exothermic. Why is it exothermic? Because normally the atoms that form negative ions, such as chlorine, is because the ion is more stable than the atom. Therefore, there is attraction between the nucleus and the electron. Then you have the second electron affinity. Same thing, but just different words. So the second electron affinity is the enthalpy change of when 1 mole of gaseous mononegative ions gains 1 mole of electrons to form 1 mole of gaseous 2 minus ions. Another example is oxygen, and this time it's not exothermic, it is endothermic, because it takes energy to overcome the repulsion between the negative ions and the electron. Sorry, I had a little hiccup there. So that's why it's endothermic. You need to remember all of this because they might put this in a 1 marker or 2 marker. And then finally, we have the enthalpy of lattice formation. So this is the enthalpy change of when 1 mole of an ionic lattice is formed from its ions in their gaseous states. Now remember what I said, take this time to remember these. Also, an example equation, sodium chloride, as you can see in its gaseous states, which is what we are going to use for our Born-Haber cycles, and it is I forgot to say that the enthalpy of lattice of formation is exothermic, meaning the arrows go down. Also guys, an exam question may ask you to calculate the enthalpy of lattice dissociation. So obviously the enthalpy of lattice dissociation is the opposite of the enthalpy of lattice formation. So enthalpy of lattice dissociation is the enthalpy change when 1 mole of an ionic lattice is separated into its ions in its gaseous form. And if the exam question asks you to calculate the enthalpy of lattice of dissociation, what you need to do is when you find the enthalpy of formation, you switch the sign of the enthalpy of formation. So for example, if it's like plus 364, then you make it minus 364, and then you add the total. And then you add the total of the enthalpy of atomization, ionization energies, whatever, in its normal signs, but you just switch the enthalpy of formation, okay, to calculate the enthalpy of lattice dissociation. And then you add everything else, and then that's your answer, basically. Okay, so after your understanding of the definitions, remembering the definitions, now we're gonna look at the important part, which is the Born-Haber cycle. Now, the purpose of the Born-Haber cycle is to calculate the lattice enthalpy of formation of a compound. I forgot to say formation. So basically, just calculating lattice enthalpy of formation. That's the whole point of the Born-Haber cycle, and it tells us the bonding strength and stability. It allows comparison with other lattices, and it also applies Hess's law, and Hess's law, which is the independent root of which it's taken to. Now we're going to look at an example. We're going to look at many examples because these could show up in any of your exam questions. So first you have a simple one. So this is sodium chloride, and we want to find the lattice enthalpy of formation. And as you remember, the definition for the lattice enthalpy of formation is the enthalpy change of 1 mole of an ionic lattice from its ions formed from its ions in its gaseous state. And here it is. So we got our sodium ions and our chloride ions in their gaseous state. So as you guys can see, I just did a big line at the bottom with sodium chloride at the bottom as well. So when we do our Haber cycles, first it starts off with the enthalpy of formation, which is from its elements in its standard state under their standard conditions. So sodium is, oh, it's not red. So sodium is a solid plus 1 mole of chlorine, which is a gas in its standard state. Okay, and the enthalpy of formation is endothermic. So that was going to go up. And there we go. Also, in an exam question, the arrow might also go down because remember the enthalpy of formation can be endothermic or exothermic. Okay, so now we want the sodium solid to be the same in the equation. We want the sodium solid to be a gas, and we want it to be a monopositive ion. First, let's change the state of making it a gas. So how can we do that? Well, we can use the enthalpy of atomization, because remember the definition of the enthalpy of atomization is the enthalpy change when it forms 1 mole of a gaseous atom from its element in its standard state. So this is sodium solid in its standard state, and then we want it to be one gaseous atom. So sodium is gaseous, and then we just leave our chlorine right there. So using the enthalpy of atomization of sodium. And then now we want sodium to be a monopositive ion. That reminds me of the definition of the first ionization energy. So remember the definition for the first ionization energy is to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of monopositive ions. And here we are. Okay. Sodium. Okay, so now we have the sodium ion. Now we want the chloride ion, and we want 1 chloride ion because there's only 1 mole of chlorines there. So that's what we want. So if we want to make chlorine a mononegative ion, we have to use the first electron of affinity, which is exothermic. So we have our sodium ion there, plus 1 mononegative chloride ion using the first electron affinity of chlorine. And then we have our arrow going down because we have our lattice. We have our enthalpy of lattice formation, which is this, because it's also exothermic. Therefore, if asked us to calculate something in the exam question, you have to know the formula. So the formula for the enthalpy of formation equals, so this equals the total of this, so it equals the enthalpy of atomization of sodium plus the enthalpy of the first ionization of sodium plus the first electron affinity of chlorine plus the lattice enthalpy of formation. So as you can see here, I just wrote the formula for the Haber cycle to calculate the enthalpy of formation here, because in order to gain at least 1 mark when answering an exam question, and it's a calculation question, if they want you to calculate, for example, they want you to calculate the atomization of sodium, you need to rearrange the equation and you need to write the whole equation to get your 1 mark in the question. And basically that's how the Haber cycle works. So whatever you eat, so for example, if there's more here and there's more here, whatever, you have to add all of them. You have to add everything in the Haber cycle to have the enthalpy of formation, which is your whole equation. Okay, next we're going to do magnesium chloride. So we have the magnesium ions, which is magnesium 2 plus Cl minus, but there's 2 chloride ions, so remember that. Okay, so as always, I'm going to start with my line. So magnesium chloride, and we're going to start with our enthalpy of formation, as we all know, which is endothermic, and then magnesium is a solid. Oh yeah, wait, sorry. And we don't need to put a half in the chlorine anymore because there's already 2 chlorine atoms because it's a diatomic molecule. So that is our enthalpy of formation. Okay, so what is next? So what can I see? What I need to do here? Okay, so I need magnesium 2 plus. So let's do the magnesium first because that's more of the easiest. So okay, so magnesium is solid, but we need it in a gas. So what do? Enthalpy of atomization, because this forms 1 mole of gaseous atom from its element. So there we go. See guys, it's all about you understanding these definitions, you know. You need to know these definitions and it becomes way more easier than you think. Okay, both in their gaseous states, but we need magnesium in its 2 plus. But first, it can go for its first ionization energy in order for it to have a 2 plus. So remember, first ionization energy of magnesium, so the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of monopositive ions, guys. Okay, so here, this is the first ionization energy of magnesium, and that's how we're going to make Mg2 plus, because now we can do the second ionization energy of magnesium, which basically same definition but just makes gaseous 2 plus ions. Okay, perfect. So now we need chlorine in its ionic state. So how are we going to do that? Okay, well, we need chlorine to just be, we need just 1 chlorine, because as you can see in this equation, chlorine is not CO2. It's not CO2 in the ionic form. There's 2 chloride ions there, 2 moles of chloride ions, but there's not a diatomic molecule of 2 chloride ions, if you get what I mean. So this big 2 just means there's 2 moles of chloride ions, but doesn't have a CO2 there. So we just want 1 chlorine. So how do we do that? Well, the enthalpy of atomization forms 1 mole of gaseous atom. 1 mole of gaseous atom. So we do the enthalpy of atomization of chlorine, and that is endothermic. So it keeps on going up. Wow, quite big actually. Okay, so there we go. Okay. Right, so now we want chlorine to be in its ionic form. Oh wait, guys, and also since there's oops, I forgot to mention, since there is our 2 here, remember guys, there's 2 chloride ions here, meaning that since the enthalpy of atomization forms 1 mole of gaseous atom, we want 2 moles. We want 2 moles of gaseous atom. Therefore, we times the enthalpy of atomization of chlorine, we times it by 2. So therefore, there's 2 chlorines, gaseous atom. Okay, so now we want this to be in ionic form. How can we do this? Well, let me just draw my box a bit bigger because we need it more longer. So, oops, sorry. Okay. So now to make chlorine negative, it needs to go through the second electron affinity. I mean, not the second, because that makes 2 9. I mean, the first electron affinity. So if you put our arrow down here, okay, see our magnesium is sorted. And then we use our first electron affinity of chlorine, but we also times it by 2 because there's 2 moles of the chloride ions. So we put our 2 there and a Cl minus. And then the last enthalpy formation is exo, so the arrows go down. And that is how the cycle works. So that's how a magnesium chloride cycle works. Okay guys, and finally we're going to do calcium oxide. Okay, so this is going to be quite a big one, so scroll down a bit. Okay, so just do my long line for calcium oxide right here. Okay, so first you start with our enthalpy of formation, as we all know. So calcium is a solid, and we only want 1 mole. We only want 1 mole of oxygen, so we do half oxygen. Even though oxygen is a diatomic molecule and it's a gas in its standard state. And enthalpy of formation is endothermic. Right, okay, so now we want the calcium to be a gas, so let's focus on the calcium. So the enthalpy of atomization forms 1 mole of gaseous atom. Actually, let me do the arrow here. Sorry. Okay, then next we want calcium to be in its ionic state. We want an ion, so first ionization energy first, because Ca is Ca2 calcium 2 plus, but first has to go through its first ionization energy. Okay. And guys, remember ionization energy required to remove 1 mole of electrons, and then okay, then obviously it's calcium 2 plus, so we do the second ionization energy. Oh, it made a red shape. It's meant to be a rectangle. Okay. Okay, so now we're gonna focus on the oxygen. So we want oxygen to be oxygen 2 minus. So what we can do is do the first electron affinity. Wait, let me make the box more longer. So there we go. So then we want the first electron affinity of oxygen, because we want O2 minus. So, and it's, remember, first electron affinity is exothermic, so the arrow goes down. So let's do this right here. Okay, and it's going to be plus an electron plus O minus in this gaseous form. And the reason why there's 1 electron, because this is how we're going to form the second electron affinity, which is endothermic. So it's going to go back up here. And let me just... And it's going to be form O2 minus, which is a gas. And the reason why... Oh wait, oh my gosh, the boxes are overlapping. Okay, so let me just quickly write this. Okay. And the reason why there's an electron here and there's an oxygen here, doing different color, is because, remember, the second electron affinity is basically formed because there's repulsion between the negative ion, which is this, and the electron, which is that, which is then energy is needed to overcome the repulsion. So therefore it forms the second electron affinity of oxygen, which is makes our gaseous 2 minus ion. So now we have our ion set, which matches our equation, if I could find it here. So therefore the lattice enthalpy of formation is exothermic, so we can put an arrow going down. It's gonna be a really big one. There we go. And that is our enthalpy of formation. And as you can see, the whole Haber cycle is going to go down like this. Okay, so you can pause the video and do the question if you want to, and see if you get it right. Okay, write an equation. So it wants us to write an equation for the process that has an enthalpy change equal to the electron affinity of chlorine. So that's basically saying write an equation for the first electron affinity of chlorine. So remember, electron affinity is when it gains electrons. So the gaseous atom gains electrons. So plus E minus makes Cl minus is a gas. Okay. And that is our answer. In terms of electrostatic forces, so just why the electron affinity of fluorine has a negative value. Okay. So if you remember what I said about the electron affinity, and it says negative value, hinting it's exothermic, hinting it releases energy. So remember that the fluoride ion would be more stable than the actual atom, fluorine. This is because there is electrostatic attraction between the nucleus positive nucleus in case, between the positive nucleus and negative electron. So it releases energy. And that's how you get your 2 marks. By saying that it releases energy, and by saying there's attraction between the positive nucleus and the electron. That's like a whole sentence, 1 mark. Okay, next, complete the Born-Haber cycle for silver fluoride. For silver fluoride by adding the missing species on the dotted lines. Okay. So this is what we need to complete. So we have our end product. The end product is this. That's our end product that we want. Okay, so first we're going to start off with the enthalpy of formation. And as what I do when I always see these, I state the stages. So enthalpy of formation. So this is 1 mole. There's 1 mole of fluorine. So half a mole of fluorine in its gaseous state. It's a standard state. Then next it goes from solid to a gas for silver. So this is the enthalpy of atomization of silver, and then the fluorine will stay the same. Okay, and then there's the first ionization energy here for silver. So write that stage down. And then the fluorine will just stay the same. Okay, and then now we're going to change the fluorine to be 1 mole. So it'll just be fluorine as a gas. And that is the enthalpy of atomization of fluorine. Okay, next. Okay, now it goes down because you want the first electron affinity of fluorine because it's now negatively charged. So this is the electron affinity of fluorine. And this is this is dissociation because arrow's going upwards. So okay. And then you will get 3 marks. So you'll get 3 marks for you'll get marks for the equations, obviously. Sorry guys, I forgot about the electron. Because remember the first ionization energy is plus an electron. My bad. Plus an electron. Okay, now it's perfect. Okay, so you're gonna get a mark for the top line being this equation. And you're going to get another mark for the second line being that equation, and then you're going to get another mark for just the bottom 2 lines. So you're going to get a mark for this, a mark for this, and just a mark for both of these. Okay, the next part is use the cycle to calculate the bond enthalpy of the fluorine-fluorine bond. Okay, now this is a bit different. Okay, and this is 2 marks only. So there's going to be a mark for the answer and a mark for just the working out. But you should just write the formula just in case. But okay. So first what I would do is that I will state, so I see my stages, right? Okay, so and then I'll fill in the numbers so I can see what's missing. So enthalpy of formation for silver fluoride is -203. Enthalpy of lattice of dissociation plus 90, so this is plus 955. Electron affinity for fluorine is -248. Okay, then this one, first ionization for silver. Wait, so 32. And atomization for silver is 229. Okay, so what is missing? The atomization of fluorine, guys. That is missing, so we need to calculate that. Okay, guys, so basically, you know the formula for the enthalpy of formation. You basically make it equal to the enthalpy of formation, which is -203, equals to the total of all of this. Now, since it's the lattice of dissociation and it's not the lattice enthalpy of formation, we have to switch the sign to -955. So it'll be -955 plus -248 plus 732 plus 289. And that's going to equal, oh, for the plus X, because that's the atomization of, what's this again? Sorry. Fluorine. Right, okay. So minus 282 plus X. Okay, now you plus 282 on both sides. That is going to be X equals 79. So that's the atomization of chlorine. I mean, is it fluorine, sorry. But we haven't finished it yet because they want the fluorine bond. And this is, so this 79 equals to like 1 fluorine. They want a fluorine to fluorine bond. There's 2 fluorines. So we do 79 times 2. And that is 158 plus. Okay, and then that's correct. We can check the mark scheme. Okay, so we can see in the mark scheme that we get a mark for working it out, calculation. And then we get a mark for 79. And we get a mark for 158. So we get our marks right here. Okay, so another question. You can pause and do the question if you want to and check if you get it correct. Okay, so the enthalpy of atomization is the, oh, not red, is the enthalpy change to form 1 mole of a gaseous atom from its element in its gaseous state. Then the lattice association enthalpy is the enthalpy change of 1 mole of an ionic lattice that's separated into its ions in its gaseous state. Now you're gonna get 3 marks. So you're gonna get, actually no, 2 marks, sorry. You're gonna get a mark for saying the enthalpy change to form 1 mole of a gaseous atom. So you're gonna get a mark for that. From its element in its gaseous state, you're gonna get a mark for that. Then you're gonna get another 2 marks. You're gonna get a mark from the enthalpy change of 1 mole of an ionic lattice. So you can get a mark for that. And then you're gonna get another mark for it's separated into its ions in its gaseous state. You're gonna get another mark for that. Okay, next question. Use the following to calculate value for the lattice dissociation enthalpy of sodium chloride. So first, I would state what the stages are. So here's enthalpy of formation. Here is the first electron affinity of chlorine. Here is the atomization of chlorine, but we're going to talk about more of that later. Here is the first ionization energy of sodium, and here is the atomization of sodium. Okay, so to calculate the lattice dissociation enthalpy, so this is 3 marks, so since 3 marks you have to write a formula. So I would say write a formula for the lattice dissociation. So if you know the formula for the enthalpy of formation, then you would know the enthalpy of the lattice dissociation enthalpy formula. You just basically, it'll be minus the enthalpy of formation. So lattice dissociation enthalpy would be like this. There would be no F because it's not formation anyway. Same thing though. Okay, and then so minus the formation plus everything else. Oops. Okay, next is the calculation. Now you need to look carefully at this here, because what is our end product? So it's sodium chloride. Our end product is Na plus and Cl minus. So that means one mole of chlorine. Here it shows 2 moles of chlorine, but we don't want 2 moles of chlorine. So let me just write this here on the side. Okay, this shows 2 moles of chlorine. We want 1 mole of chlorine. That's what we want. So that's by dividing by 2. Divided by 2, that'd be half of chlorine then. So then, since this is plus 242, then if you also divide by 2, that's going to be plus 121. So that's what we're going to use, because that's for 1 mole of chlorine. We want 1 mole of chlorine. So now we just calculate it as usual. So we do the opposite sign of the enthalpy of formation, remember, to calculate that stuff dissociation. So it'd be plus 401 plus literally everything else. Oh, plus 121, because that's for 1 mole of chlorine. Plus 484 plus 109. Okay, that's it. So then this would equal plus 771. Now you need to write the plus. So you're going to get a mark for the answer, you're going to get a mark for your calculation, and you're going to get a mark for your formula. And that is your 3 marks.